All right, well, we're going to go ahead and get started. So today we have your final exam prep. So what is the study of the rate of reactions? And that's going to be kinetics. Over here. And at what point, or the point at which forward and reverse reactions rates are equal, what is that going to be? And that's going to be our point of equilibrium. Our electron pair acceptors, what is that going to be? It's going to be our Lewis acid. And our electron pair donors, exact opposites here, that's going to be our Lewis base. A solution with weak acid and its conjugate base, or vice versa, that resist change in pH. And that is going to be sorry, took a little much out there. It's going to be a buffer. And what is a hydrogen ion acceptor? That's going to be our Bronsted-Lowry base. And our hydrogen donor is going to be our Bronsted-Lowry acid. The release of hydrogen ions in water, what is that going to be? So that's going to be our Arrhenius acid. And the opposite of that, releasing OH minus ions in water are hydroxide ions, and that's going to be our Arrhenius base. Now we're going to look at what is a reaction that will proceed without outside assistance. A reaction that will proceed without outside assistance, and that's going to be spontaneous. What is the idea that reactions will do what's necessary within their power to remain at equilibrium? And that's going to be Le Chatelier's. And I probably butchered that name, apologize. Principle. List 4 colligative properties. And that's going to be our vapor or our osmotic pressure, vapor pressure lowering, freezing point depression, and boiling point pressure. So actually I already had that on here for you. Here, we'll go and put that in a fun color. Use purple today. Oh, we highlighted it. I guess that works too. So we have vapor pressure lowering, osmotic pressure, freezing point depression, and the melting point elevation. And so that's what is going to change whenever you add more of the colloids or like a substance that dissolves in a solvent. When you add more solute, that's what's going to happen is these things. So like the vapor pressure is going to decrease, it's going to lower. You have the osmotic pressure and how that's going to change. You have the freezing point, that's going to get lower, it's going to depress. And the melting point, that's actually going to get higher. So, and then also one that this one I believe is actually, we also have boiling point elevation. For the other one there. Find the molar mass of lipase given that 23 grams of lipase dissolved in enough water to make 1 liter of solution exerts an osmotic pressure of 4.7 torr at 20 degrees Celsius. And remember that 1 atm is equal to 760 torr. So go ahead and look at that here. We're gonna change that to our fun color and move this over. Okay, let's match it with that one actually. So we look at this, we're going to have, let's look at what equation we're going to need to use first. So our general equation is going to be, get the pi symbol here. It's going to be capital Pi, which looks like that, or sometimes it looks more like a table, like a line going across the top. I'm not seeing one that looks exactly like syncing up. Okay, so we're going to have pi equals, and that would be equal to IMRT. But what we're looking for is the molar mass, and you would get that from finding the number of moles, which is going to be part of your osmotic pressures, because that's in your moles, not your osmotic pressure, that's going to be part of your M. Sorry, said the wrong one. You need to switch it around. It's going to be part of your M because that's your molarity, so moles per liter. So we're going to go ahead and switch that around just to make life easier. So it's going to be M equals pi over IRT. So we can go ahead and see what we know to go ahead and start figuring that out. So we know we have our osmotic pressure in torrs. So let's go ahead and turn that into ATM, and then we can go ahead and put that on there. So we'll go over here and work on that. So we're gonna have 4.7 torr. And then if we multiply that by 1 ATM per 760 torr, then we can go ahead and solve that. And if you go ahead and do the math, you should come up with that equaled 0.0062 ATM. So we can go ahead and plug that in because this is going to be our osmotic pressure here. So we have that 0.0062 ATM divided by everything else. So we're going to have I, and lipase isn't going to dissociate in water into different ions or anything, so that's just going to be 1 for I. Then R, which is our constant, and we're going to use 0.0821 liters times ATM over our over mole K times our temperature. Okay, and then we're going to multiply that by our temperature in Kelvin. So that's where you do your math and convert your Celsius into Kelvin, where you do 273 plus our 20, and we come up with 293 Kelvin. And then you have everything there. So if you go ahead and solve all of this out, and I like to do the math all at once in the calculator so that you don't end up with any rounding issues or anything like that. And once you do all of that, you come up with 2.58 molars or moles per liter. If you go ahead and cancel your units out here, you'll see that. So we have ATM here. We have ATM here. Then we have Kelvin and Kelvin. All right, so then we're left with liters per mole, but this is all underneath, so that actually switches around to make it moles per liter, and that's where we come up with that. So we have moles per liter. Okay, but what are we looking for? We're looking for the molar mass of lipase, and we know that we have 23 grams of that in 1 liter. So if we have 23 grams of lipase per 1 liter, and then we take that and we divide it by our what we just came up with here, our moles per liter. Go ahead and divide it by that. So I'm just going to make this grams per liter since it's just per 1 liter. Makes that a little easier to visualize. Okay, so we're going to see that our liters are going to cancel out. here and here. Okay, and then we're going to end up with 23 divided by 2.58, and then we'll end up in molars or in grams per mole like we wanted to. So if we do this math, we end up coming up with wait a second. Oh, okay, that's what I did wrong here. Okay, so I forgot to put in, if you're following along on your math, you would have caught this. Sorry about that. This is times 10 to the negative 4. Okay, so whenever you do that and solve this out, you're going to end up with 8.915 times 10 to the negative 4, or 10 to the 4th, not negative, 10 to the 4th, and that's going to be in grams per mole, which is going to be your molar mass. And there's going to be your answer. So here it is. So we can go ahead and move on to our next problem. So we're going to determine the vapor pressure of water at 25 degrees Celsius in a solution prepared by dissolving 14.5 grams of fluorine in 58 grams of water. The vapor pressure of water is 25 degrees Celsius at 23. Yeah, the vapor pressure of water at 25 degrees Celsius is 23.84. Sorry, stumbled on my words there. So go ahead, change this again. So we're going to go ahead and get this started. So if we're needing to find the vapor pressure in a solution, okay, so we're going to find the vapor pressure here. So we're going to have P of the solution or we can go ahead and shorthand that actually. The solution is going to be equal to the mole fraction of the solvent times the pressure of the solvent. Okay, so we can go ahead and work this out, see what we know. So we're going to keep this here. So what is the mole fraction of the solvent? We need to figure that out first. So if you remember, the mole fraction is going to be the total, it's going to be the moles of the solvent over the total moles. So we have moles solvent over total moles. And switch that around. Okay, so we're gonna look and see how many moles of solvent do we have. So we're gonna need to figure out how many moles of each of these, and they gave it to us in grams. So let's go ahead and solve for that. So you're just gonna find your, I'm sure that you guys should know this by now, but just a refresher, you need to find the molarity, or no, it's molarity, the number of moles. You're just gonna go ahead and do this divided by this to get it for the fluorine, and the 58 grams divided by 18.02 grams per mole for the water, and you'll be able to find them that way. So whenever we go ahead and solve this, we're going to have x equals our moles of water. So we're going to have 3.219 moles of water divided by and so we're going to have our 3.219 moles of water plus, when we solve out for the fluorine, we end up with 0.0805 moles of that. Okay, so then you're going to go ahead and solve this out. And so you're going to have x equals, and you're going to should come up with, and it's going to be pretty high because you look at that is a significant portion. This is really small in comparison. So you're going to come up with 0.9756. And you don't need a unit because your moles cancel each other out here. So there's our answer for that. Okay, then we're going to go ahead and multiply that by the P of the solvent. So they gave us that. That's our 23.8 torr here. So this is going to be 23.8 torr. And so we're going to go ahead, solve that. And you should come up with 23.22 torr. And that is going to be your answer right there. All right, on to the next one. We're going to determine the boiling elevation of water in the solution prepared by mixing 439 grams of benzaldehyde with 837 grams of water. The boiling point of water is 100 degrees Celsius with a Kb of 0.52 Celsius per mole. Okay, so we're going to go ahead and solve that. So if you remember your equation for your this here, I'll get that put up here in just a second, but that's going to be your delta, so the change in temperature when it boils times I Kb times mole. So let's go ahead and get Let me get a delta symbol real quick. So we're going to have delta T, so change the temperature when it boils. And that is going to be equal to I times K B times molal. Whoops, not molarity, molal. Okay, so let's go ahead and fill in what we know. So we're solving for this right now. And so I is going to be 1. Typically it is, so if you can't figure it out on your exam, just go ahead and put 1. Sometimes it will be different though, and that's going to be if it's something that's going to break apart into different ions or something like that. So if it's like electrolyte or something, then it won't be 1, it'll be greater than that. It should always be a whole number though. Okay, so then we're going to have our KB, and they gave us that. So we have that right here. Right? Then we're going to multiply that by the molals. Okay, so if you remember, molal is, so that's our little m, and that's going to be equal to our moles of solute over our kilograms solvent. Okay, so we're going to go ahead and have to do our molar mass, or we're going to have to use our molar mass to figure out what the number of moles of our solute are. So we know water is going to be our solvent. So let's go look at our benzyl hydride. So that would be, to find that, you do your 439 grams of your solute divided by your molecular weight here. Your grams cancel out and you'd have it in moles. Okay, and so if you go ahead and do that, you should come up with 4.137 moles. And we're going to divide that by the kilograms of solvent. So the kilograms of water. So we have it in grams here. So we know to put that in kilograms. We're just going to have to move our decimal place 3 times to the left. So we're going to get our 0.837 kilograms, right? So after all of that, you're going to have your M is going to be equal to 4.943. And remember that is moles per kilogram or just M. Either one is fine. And since in your problem it just has it as M, I would just keep the unit the same. So we can go ahead and plug that into our problem now. So I'm going to go ahead and move these over because they're kind of close too. And that one will end up being moved in a second. Okay, so now let's figure out what this is then. All right, so when you go ahead and do all of your math for that, you should come up with 2.57 degrees Celsius. Okay, but so that's your change in temperature. So we look at the boiling point of water, which you should know is 100 degrees Celsius, but they also gave it to you up here. And so we're going to take that 100 degrees Celsius and we're going to add the change in the boiling point. There we go. Plus are 2.57 degrees Celsius. Okay. And then you're going to have your total. So our boiling point is going to be equal to 102.57 degrees Celsius. And there's your final answer. For the following reaction, H2 is consumed at a rate of 0.06 moles per second, or molars per second, sorry. Determine the rate of NH3 production and N2 consumption. Okay, so go ahead and work on this. How many lines? I'm going to move this up a little bit so we don't end up running out of space on our page here. Hopefully that's enough space there. Okay, so that. Perfect. Okay, so for the following reaction, H2 is consumed at the rate of 0.6 moles per second. We're determining the rate of NH3 production and NH2 consumption. So this is one we're going to look at it based on your stoichiometric values. And okay. Okay, so I stopped and took a minute and actually set this up to where you could see it a little bit. So these are, like I said, based on the stoichiometric values. And so what we're kind of going to look at is this here. So we have our delta, and the change in concentration is on the top for each of them, and it's going to be on the bottom, and then the change in time is on the bottom. And overall, these are all going to be equal if you, I guess I probably should have put this on the bottom, but it's if you divide them by their number of moles times, but you can see it's so it's like the change in concentration over the stoichiometric value, so it's coefficient, so 1 times T there. And same thing here, got your concentration, the coefficient there. So we know that this one, overall, that the rate of consumption of that is 0.06 molars per second for H2. So let's see. So we have H2. Is going to be equal to that. Okay. And so to figure out the other ones, what we're going to do is it'd be like if you plugged in, because the seconds are all the same across the board, so we can kind of ignore that. So it's like you just plugged this in for the molarity. So like if we plug this in for H2 here, so if we plugged that in as this 0.06 and then went ahead and just used that to solve, so you can see that if we went ahead and moved that around, we would end up with here, so we'd end up with the concentration of N when we go try to find that. It's not gonna let me do that. So we're going to see that the concentration of N, that change in concentration, which I'm just going to put into for simplify things, is going to be equal to the concentration of H2, so our 0.06 molar per second divided by this 3 here, divided by that coefficient, divided by 3. And so if you go ahead and solve that out, you get that it's going to equal, sorry, I just like to look at that. So you get that it's going to be equal to a third of that, so it's going to be 0.02 molars per second. And that's going to be the rate of consumption for N2 here. Okay, so now we're going to go look at NH3. So for NH3, it's going to be stubborn. So for NH3, we're going to have, and that's going to be equal to, oh, this is not supposed to, okay, so we're going to have our 0.06 once more. So, and but we're going to have to, so this was NH3 over 2 is what it was basically, times and the time, but the time's the same problem, so we're not worrying about it. So we're going to have to multiply by that too. So we're going to have 2 times our 0.06 moles per second divided by 3. Okay, so we already know this part. And honestly, if you wanted to, you could have just gone from that because you already know what this here equals. You know that equals your 0.02. So you could do that either way. I'm just going to go ahead and leave it though, or I can show you that too, I guess. So that's 2 times your 0.02 moles per or molars per second. Okay, and so that is going to equal your rate of production for your NH3, and so you're going to end up with 0.04 molars per second rate of NH3 production. All right, so we can go ahead and move on to number 7. For the following reaction rate, information provided, the rate law, rate constant, and overall reaction order. So we can go ahead and look at this. So let's find how, we'll look at them, I guess, in order here. So if we're looking at how the rate for, or how ClO2 affects the rate, let's look at its effects. So we're going to look at this, and so let's compare reactions 1 and 3, because that's where F2 stays the same. Okay, so we're going to compare 1 and 3 here. So let's see. Okay, so when we do that, we see that going, sorry, I have to plug this in. It isn't dying. Okay, so we see that we have from 1 to 3, it does not change for F, that's why we're using that. Whoops. And then, so we're going to look from here to here. So it doubles here, okay? And we're going to look over here, and we see that that quadruples. So 2 times, 4 times. So what is that? That is going to be 2 to the x. Okay, so that's where you do, where it is like this. You have 2 to the x. We'll do that. So we'll do 2 to the x equals 4. And then you have to solve for x. So 2 squared is going to be 4. So we're going to have x equals 2. Okay, so now we're going to look at I guess we can leave those. That doesn't really matter, honestly. So now let's go ahead and look at our F2 here. So we're going to compare reactions where this doesn't change and this does this time. So it doesn't change between experiments 1 and 2. So let's compare experiments 1 and 2. So when you look at that, okay, so from 1 to 2, from here to here, it's going to what? It quadruples, okay? So we're going to have 4 to the y. Okay, then that is going to equal what? Okay, so what can, how it changes here. That's also going to be a multiple of 4 there. So that's going to equal 4. All right, so that's going to leave us with y equals what? And that's going to be 1. So we see that the concentration of F2 doesn't actually affect the reaction. So there is that. So let's go ahead and write out the rate law formula. So we have rate law equals, so we have this concentration here. It's going to be K times that, control V. And that's going to be squared. Oh, and I told you guys wrong. This does have an effect on the rate. You just don't have an exponent. That's what I meant to say. Unless it's 0. 0 is the only way it means it doesn't have an effect on the rate at all. Is if that y were to be 0, because then it would remove it from the equation. Okay, so there is our rate law. But we need to figure out what our rate constant is so that we can figure out our what this K value is and go ahead and plug that in. Okay, so to do that, we are going to go ahead and plug things in. So rate law, or just the rate, is going to be, so let's just go ahead and use the first reaction because it's easiest, got the smallest numbers. So we have our rate of this right here. All right. And that's going to equal K. Or actually, I like to rearrange things first, so let's do that. So we would end up with, if we do that, K equals the rate is actually on the bottom. So it's going to be equal to these over the rate. Here, I'll go ahead and put that in. So we're going to have K equals this divided by rate. Right? So here's our rate. So you got what goes after the division sign there. Okay, so concentration of ClO2, and that's going to be 0.10, 0.1 squared times the concentration of F2, so 0.010. Okay, so you go ahead and solve that and you'll figure out your value for K. And if you go ahead and do your math for that, double check my math. Oh shoot, that's because I told you this completely backwards. This is the rate divided by the other. I'm sorry, guys. That backwards for you. So okay, so that's going to be rate divided by that, and that might help this here. Okay, that makes more sense now. I was looking at my numbers and they did not look right. So then you do that and you end up with your rate equals 12. All or not your rate, your K value, your constant is 12. So we can go ahead and plug that into this equation right here. And K value is 12. Okay. So this is going to be our rate law. Is that okay? So we found that. We found the rate constant, our K is 12. And now let's look at what the overall reaction order is. So the reaction order, remember, is if you add up your exponents. So we have 2 plus our imaginary 1 here, 2 plus 1, so 3. Our reaction order is 3. All right, there you go. These will be your answers right here. Here are the questions. What are the equations for a first and second reaction order? If shown a graph, how can you tell whether or not a reaction is first or second order? So okay, sorry, forgot to do that earlier. Okay, so first off, we're looking at a first order. Let's start. A first order. Then our equation is going to be the natural log of A. And if we're looking at second order, our equation is going to be 1 over A. All right. So, let's see. See if I can pull you guys up a graph real quick. Just a second. Yeah, and then you guys can see it because I can't really draw that on here for you. Okay, this will work. Okay, here we go. Go ahead and get y'all a picture, which is way huge. Here we go. Don't need all of that. So here we go. Go ahead and do this. Okay, and that'll show you a zero order also. But there you go. You guys have some graphs you can look at now to kind of see those values a little bit. Okay, so we have a 0 order reaction, first order reaction, and a second order reaction. And so that's how you know if they are like a first order or a second order reaction, is if you have that linear graph whenever you put that reaction versus time, or put this equation versus time. So first order, you put the natural log of A, have the concentration of A versus time. That's what you come up with. All right. All right, so let's look at this one. The rate constant K1 for a reaction is 4.23 times 10 to the negative 9 per second to the negative 1 at 298 Kelvin. What is the rate constant K2 at 350 Kelvin if the energy of activation is 6.14 times 10 to the 4th joules per mole, and R is 8.314 joules per mole K. All right, so first off, let's look at our equation. And there we go. It's just a little bit more space here. Okay, so go ahead and move this over and make it purple. Okay, so our equation is going to be K equals the A E times negative energy activation over RT. All right, so let's go ahead and start plugging in what we can. And so we're going to be solving for A, but this is one that's a little bit strange to just go ahead and start rearranging. So, but I guess we could. So let's look at this here. Okay. So our rate constant, that's probably little k, is going to be 4.23 times 10 to the negative 9 per second. And that's going to equal A times E I put that in here wrong. Sorry, this is supposed to all be here. Okay. So let's go ahead, I guess, and move things around. I think that would make this a little bit easier, just because you won't have to write so much stuff up in an exponent that way. So if you go ahead and look at this. Okay, so if we take the natural log of both sides, then it's going to cancel out that E. So we're going to end up with a times all this. All right, so then we can just go ahead and do the, to get a by itself, we can go ahead and do the natural log of k divided by all of this, right? So if we do that, we'll have natural log of a equals natural log of k divided by negative energy of activation, or RT. So I'm going to go ahead and put that on the bottom. I'm going to put everything else on top though, because that puts it under 2 of those. So I'm going to put RT on top. All right. So now we can go ahead and solve this and just makes that a little bit simpler. So let's move that back over. Sorry. Okay. So we're going to have the natural log of this. So that's our k value. Oh. All right. So the natural log of that times R. It gave us R, so 8.314 joules per mole times Kelvin. All right. And then multiply it by our degrees in Kelvin. And this was at 298 Kelvin. Oh, whoops, sorry, where did I get that? No, that's right, Kelvin. Yeah, I can sure. Okay, and then we're going to go ahead and divide that by our energy of activation, which seems to have lost the 0. So our energy of activation is right here. Okay, it doesn't want to work with me. Sorry. Okay. And all right, so divided by that. So you can go ahead and just solve all of that out and however is easiest for you, but that's how I like to do it. And you should come up with A equals 245. Okay, so now we're going to take this A and we're going to plug it into the equation for K2 to figure that out. So if A is 245, we're going to go ahead and we're going to look, we're trying to find K. So this is a great equation this time. So we're going to do that. So we have let me see. Okay, there's a few more lines here. So we're going to have K equals A, so 245 times e to the power of the energy of activation, which is going to remain the same. So just going to be this right here again. Okay, so we're going to put that here. Okay, and all right, so we have our energy of activation divided by our RT. So R is still going to be this right here. And it's just going to be stubborn form. Sorry. Right? Times RT value, so 350. All right, and then you just solve all of that out to get your K value, and you're going to end up with K is determined to make capitalized equals 1.68 times 10 to the negative 7. Sorry, that problem took quite. Okay, so a first order reaction has an initial concentration of a rate, initial concentration of a reactant equal to 0.5 molar. The rate constant is 5.8 times 10 to the negative 4 s to the negative 1. Calculate the concentration of the reactant after 625 seconds. So and change it to purple. Do that. All right. So we're going to have the concentration of A, for equation here, is going to be equal to concentration of A initial E times E to the negative KT. All right. So what do we know? We're going to have the concentration of A again equals what it is initially. So 0.5 times E to the power of negative K. So negative 5.8 times 10 to the negative 4. S to the negative 1. Yeah, our unit's S to the negative 1 or 1 over S. I'll just put 1 over S for simplicity up here. remember S times that are 625 seconds. So seconds there are going to cancel out, as you can see with that. And we're going to end up with concentration of A equals 0.348 molars. Okay. First order decomposition reaction has a reaction rate of K equals 4.87 times 10 to the negative 4. With seconds to the negative 1, calculate the half-life. Okay, so our half-life reaction here is going to be T1/2 is equal to onto over K is, okay, so we can go ahead and solve that out. And if you remember the negative log, or not negative, the natural log of 2 is going to be our 0.693, and use that quite a bit. So you can remember natural log of 2 or 0.693, either one's fine, over K. So this right here. Right? And you solve that, get your half-life equal to 1.423 seconds, which if you put that in scientific notations, that's going to be 1.423 times 10 to the third seconds. All right, on to number 12. Calculate the reaction quotient for the following reaction when there is 0.45 moles of Cl minus and 0.98 moles of Pb2 plus in 5 liters of solution. All right, so we're doing reaction quotient. So our reaction quotient is going to be oops, we got some weird formatting going on in this one. Okay, reaction quotient. It's going to be Q equals, and it's going to be our reactant, or our products over our reactants, remember? So our concentration of Pb 2 plus, oh, let's capitalize that. Times the concentration of Cl minus squared all over concentration of PbCl2. All right. So there's that. Okay, so, oh, actually, I apologize. We do not include our PbCl2 in this because it is a solid, and remember we only include aqueous, or I believe it's gases in this. We don't include solids or liquids. So we don't include that. Okay. Also, I'm not sure why that didn't move the rest. Okay, so go ahead and solve that. And they said it's in 5 liters of solution, so we can honestly go ahead. No, we do have this right. Okay, so we now have our Q equals 0.45 over, that's our moles per liter. So for our 5 liters, times, oh, whoops, I switched those. This is our 0.98 because this is the times all this again, 0.45 moles per 5 liters closed and squared. Okay, so then you're going to solve that to find your reaction quotient. It should equal 1.59 times 10 to the negative 3. All right, on to number 13. Is there a precipitate present in the reaction above if the KSP is 1.6 times 10 to the negative 5? And so remember that if Q is greater than K, it's saturated and therefore there's precipitate. If Q is less than K, it's unsaturated and there's no precipitate. And if Q is equal to K, then it's at equilibrium and it's saturated, but it's at the point where it's about to form precipitate, but there's not one yet. So we're going to look at this. So is Q bigger or smaller than K? We can see that it's significantly larger because that negative 3 compared to that negative 5 there. So because Q is greater than K, so there is a precipitate. So yes, there is a precipitate. If Q is less than K, which direction will the reaction proceed? And so if Q is less than K, then it is going to shift toward the reactants. No, shift toward the product. Sorry, I said that backwards. So let's go ahead and put that in here. If the value of KQ for the following reaction is 794 at 25 degrees Celsius, what is the value of KEQ for the new reaction concentrations? So we're going to look at that and we're just going to kind of see how they compare. So if you think of your KEQ, like we talked about a minute ago, it's the same equation as it would be for if you had the Q value up there, it's just at equilibrium. So it's going to be our products over our reactants. And you're going to look at the difference here. So this is, everything is just doubled. So we can just go ahead and put in a 2 for everything. And so since everything is doubled, it's like where you would basically have to square it to get to that, because of you know how like if you had in this one you would just have, you know, like hi squared over h times I. Well, in this one it would be hi to the 4th power over h squared times I squared. So you can see that it's like everything has been squared from here to there. So we're also going to square this, and that's what your difference is going to be. So what we're going to do is we're just going to do, turn that purple. It's just going to be 794 squared. That's it. That's all you're going to have to do. And so that is going to be equal to 6.304 times 10 to the 5th power. All right, number 16. If you increase the volume of a container with a gaseous reaction at equilibrium, which direction will the reaction shift to maintain equilibrium? What will happen to the same reaction if the temperature decreases? All right. So you increase the volume, which direction will go? So an increase in volume is going to make everything want to spread out, right? So how I like to look at that is it's getting bigger. So if you increase the volume, the pressure is going to decrease, and in turn, you're going to have everything's going to want to end up going toward where there is more moles, so it can spread out more because of that. So increasing is going to equal whoops, I cannot spell, sorry, toward side with more moles. Okay, so which direction will shift to maintain equilibrium? What will happen to the same reaction if the temperature decreases? So if we decrease temperature, then decrease the temperature, it's going to want to shift toward the side with fewer moles, I believe. Let me double check that quick so I don't tell you wrong. So I looked into that. So this is going to be based on whether it's endothermic or exothermic. So if it is endothermic, it'll shift left. And if it's exothermic, it's going to shift right. So it's going to shift toward the side with guess with less heat inside the reaction. That's what it's doing there. So how do you produce a conjugate acid or base from a given compound? And usually, a lot of them, this will work with. This isn't, you know, a rule that works for absolutely everything, I guess. But so if you have your base and you add H plus, you should get an conjugate acid. And if you have an acid, and you remove H, you have an acid, and you remove H plus, then you'll get a conjugate base. If you would, I guess, like an example of these, we can go ahead and put one in here. So if we have NH3, sorry about that, NH, all the wrong buttons, I'm sorry. Okay, so you have NH3. Oh, mine, that must have been hit. I don't know what happened now. 3. Okay, sorry, my numlock was off. That's what was messing it up. Okay, and then you add hydrogen. Okay, then you're going to end up with NH4 plus. And over here, you have H2SO4, and you remove a hydrogen. You end up with its conjugate base, which is HSO4 minus. Determine the pH of a 0.67 molar solution of NaOH. So to do that, we're going to have to first look at this here. So we have the concentration of O minus because it's a strong base, so it's going to completely separate out into Na plus and OH minus. So we can go ahead and use that. So we know we can use that to find our POH. So if we have our POH, we can find that by doing the negative log of ROH, right? ROH minus. You write OH for the sake of time. So, and that's going to equal the negative log of 0.67, which is going to equal 0.174. And so now we have our POH. So now to find pH, we can do 14 minus POH. So we can do 14 minus 0.174, which is going to equal 13.826. And there you go. I believe we should actually truncate top one to your decimal places. I'm thinking the rule with logs is, since we took a log of something with 2 sig figs, we need to have that many decimal places. Could be remembering that backwards, but I think that's how that works. Find the hydrogen ion concentration if H2SO4 has a pH of 2.6. So once more, move this over for you. So we're going to have, we know our H plus concentration is going to be equal to 10 to the negative pH. And we know our pH. So that's going to be 10 to the negative 2.6, which is going to equal 0.0025 molars. And there's our hydrogen ion concentration. Number 20. The Kb of NH3 is 1.77 times 10 to the negative 5. Calculate the pH of 0.750 molars of aqueous solution of NH3. So this is one where you would set up your rice table to make life easier. So all right, so we're gonna have a rice table. Okay, so we're gonna have a reaction. So NH3 plus water, but we don't have to write that because it's not gonna be important in this. And that's gonna get NH4 oh good, it's still here. I thought we lost it for a second. And stop share and restart that to make sure I didn't mess something up. Okay, cool. So we're gonna end up with this here, NH4 plus and it's our OH minus. Sweet. So our NH3, we start out with 0.750 molars that okay, and we don't know how much we start with of these others, so we just assume it's 0. We just don't know. Okay, so then over here We're going to decrease that by x, and we're going to add x to both of these sides for our change. All right. And then at equilibrium, we can just do our 0.1750 molars, or not 0.750 molars, because we're just going to ignore that x anyway, because it's going to end up being such an insignificant amount. In the long run, this is just going to be x, and this is just going to be x as well. Okay, so we have that, and we know that so we're calculating the pH. So we need to find our pOH value. They gave us the Kb, so let's go ahead and use our Kb equation here. So we're going to have our Kb going to be equal to the concentration of NH4 times the concentration of OH minus divided by concentration of NH3. So, okay, so we can go ahead and plug in what we know. So we're going to have Kb is equal to NH4 and an OH. We don't know what either of those are, so that's just going to be x squared, because that's all we know from right here. Then that's going to be divided by 0.750. Okay. Oh, and we knew our Kb. Sorry, I didn't put that in there. Here's our Kb value right here. All right. So you can go ahead and do the math for that, and you should come up with value of x equals 3.64 times 10 to the -3, which is equal to our concentration of our OH, right? Okay, so we can go ahead and use that to figure out what our pH is going to be. So we can do pOH again, same formula as we used right up here. We're going to do this exact same thing again. If I can steal that much of that. Okay. And then so I'm going to plug this number in there. Okay. Oops. And you should get answer that. I guess I did not write down. Okay, let's go and sell that real quick. Okay, so you should get answer of 2. Oh, there it was right there. I just didn't miss it when I looked. 2.44. All right, that's your pOH. So now we're gonna do the same thing we did again up here, where you do your pH. Find it there. Okay. All right, so we're going to subtract this right here. So we're going to end up with a total of 11.56 for our pH, and there's your answer. All right, I've been building this for y'all. That's most of them. Cool. Okay. Describe the pH scale, including numbers and labels where acids and bases go. Which side has a larger OH? Minus. All right. So we go ahead, look at the pH scale. I could just get you all a picture. I was gonna just kind of type it out, but why not? All right. So some kind of simple one feel. This will work. Okay. At least it's not gonna work. Cool. There it goes. Okay. You don't need it near that big though. And remember, alkaline just a fancy word for basic, basically. Okay, so you guys can kind of see it here. So, 0's on one end, 14's on the other. Got neutral at about 7 here. And you're gonna have more H plus on this end. I wonder if they'll let me type. I don't know, it doesn't matter. Sweet. Okay, so we're gonna have more H plus on this end. And we're gonna have more OH minus on this end. Okay, so we have a buffer solution containing 0.4 moles of a weak base and okay, 0.4 moles of a weak base and 0.2 moles of a conjugate acid in 1 liter of solution. Find the pH of the solution. So first off, going to find our pKb. And our pKb so our pKb, we'll find that first. pKb. And that really needs to be a little p. Okay, so that's going to be equal to negative log of our KB, because they gave us our KB right there. Okay, so let's go ahead and do that. Negative log of this right here. Right? And that is going to be equal to 4.89. All right. So we have our PKB. So now we can go ahead and do our Henderson-Hasselbalch equation, which is going to be our POH is going to be equal to PKB plus log of constant log of the concentration of our conjugate acid over the concentration of our base. Okay, so that we're going to end up with 4.89, where we just solve for that above, plus log of concentration of our conjugate acid. So we had 0.2 moles of conjugate acid. Nope. Okay, so we had 0.2 over, and then 0.4 moles of weak base. So 0.4. All right, and then if you solve that all out, you should end up with 4.589. And that is our POH. So now we can go ahead and find our pH. So pH is equal to our POH minus 14 minus our POH. Our POH, and so we're going to have 14 minus 4.589, which is going to equal 9.411. And there's your pH. If 0.02 moles of KOH was added to increase the above solution, what would the new pH be? Right? So literally, to find that, all we're going to do, we're going to take this right here. I'm just going to start with that. And okay, so we're going to start with that, right? Okay, but so we're adding 2.02 moles of KOH, right? So this is a strong base, so it's going to completely dissociate. So that means we have 0.02 moles of OH minus is what that's going to end up causing. So that means we're going to have more of our base here. So we're adding to this plus 0.02. And so we have to subtract it from our acid. 0.02 is what that's going to mean. So you're just going to solve that exactly how you just did a minute ago, except you get a different answer, obviously. So then we're going to end up with 4.522. And then Gonna go through this whole thing again. Oh, sure. Okay. And then we're going to come up with our answer of 9.478. Okay. What was the solubility of PbCl2 and a 0.5 molar solution of HCl? The KSP of PbCl2 is 1.6 times 10 to the negative 5. All right, this one is going to be another one of those lovely rice tables. Okay, so get all this where it's supposed to be. Okay, so I have a rice table here. RIC, cool. Okay, so we have PbCl2, and that is going to dissociate into, and really when I'm drawing, I think everywhere in this assignment or this worksheet where I've drawn this arrow, it's really supposed to be a double-sided, or where you have the double arrows going back and forth, but I don't remember how to do that in here, and I always forget, so I just put the regular arrow. Faster, easier, the majority of the time. And then that's going to dissociate into Pb2 plus, and into 2Cl minus. All right, so we don't care about PbCl2 at this point. We're just looking at these others. It doesn't tell us what this started with, so we just assume nothing. It's 2Cl over here. It tells us it starts with 0.50 molars. So we'll go ahead and put that up there. Then, so change. We assume it's minus x on the other side because that's what it started with. And then, so we have plus x here. And then we're going to have plus 2x here because of our stoichiometric values. Okay. Then this is just going to be x. And this is just going to be 0.5 because we're just going to ignore the x. 0.5 molars. All right. So now we can go ahead and work on solving this. All right. So we can just go ahead and use KSP because this is a solid. And we know that because we're asking about the solubility. So we're going to use our solubility product, KSP. Okay, so our KSP is going to be equal to the concentration of this one times, times the concentration of Cl minus squared. Okay. So, yeah. That's going to end up being equal to x times 0.5 squared. Okay. And that's going to end up being, that doesn't really matter. So then you're just going to solve for x. So we're going to have x equals 6.4 times 10 to the negative 5 which is all we need to look for. That's going to be your answer here. Oh, whoops. I need to go ahead and put that another line. Sorry. Let me move this real quick. This needs to come down here, actually. Okay, so this is going to be your KSP. Sorry. Forgot to put that in. You didn't have any information to use to solve for X. You looked at it that way. Okay, so if you solve for that, you should be able to get an X value of this, and that's all it's asking for, is just this right here. You're good to go? Okay. Delta G at 298 Kelvin for this reaction. Is that? Let's see. What do we have left? Okay. We are actually out of time, so I'm gonna go ahead. I'll go ahead and put the answers for the rest of them. You can do them for practice if you'd like, but that is all that we were able to get to. I'm sorry, it's a lot slower going through things on the computer, but I'm gonna have to go ahead. So, good luck on your final exam.